Hello everyone, let me introduce my group member first. It's me, Jitong, and Juan. In this part, I will quickly introduce the problem setup and then walk through the main things we did to improve the predictive performance of our models. So the goal of this project is to predict the medical insurance charges based on individual characteristics, like the age, the BMI, the smoking status, and the region. Since the outcome we are predicting is a continuous variable, we treated this as a regression model, and we mainly evaluate models using the mean square errors. We first start with some simple baseline models, including the linear regression, the region, and the lasso. These models are easy to understand and interpret, but they have relatively high errors. That suggested that the relationship between the features and the insurance costs is probably quite nonlinear, and that simple linear models weren't flexible enough. To improve the performance, we then tried some more flexible, the tree-based models, such as the random forest, the gradient boosting, and the XGBoost. Among these options, the lasso one consistently gave us the lowest validation RMSE, so we focus on that as our main models. One of the biggest performance improvement came from applying log transformations to the target variables. Insurance charges are very high-scored, means that most people have relatively low cost, but a small number of cases have extremely high costs. By modeling the log of charges instead of the raw value, the model was better able to handle this skewness and was less influenced by extreme outliers. We also used a pre-processing pipeline that standardized the numerical variables and one hot encoded categorical variables. This helped make sure that all the models were trained on clean, consistently features, and it has also reduced the risk of data leakage during the cross validations. Finally, for the more complex model, we used the regulation eyes and early stopping to help control overfitting and improve how well the model generates the new data. Overall, by combining the tree-based model with a log-transformed target and the proper pre-processing pipeline, we were able to achieve good predictions.
And the next， 好不自然啊！我滑一下。
好美呀，老婆。
好美呀，宝宝。和你一样美丽。And the next, how we validated the model, used the learning curves. In this section, I will focus on how we evaluate our models and checked whether the final model was underfitting or overfitting. We started with a standard training validation split to compare different models using metrics like RMSE, MAE, and R-squared. However, we realized that relying on a single split can be a bit unstable, since the result can change depending on how the data is split. So for our best performing model, which was XGBoost, we also applied the 5-fold cross-validation. Cross-validation gives us a more reliable estimate of how the model would perform on unseen data. And it showed that the RMSE was fairly stable across different folds. This gave us more confidence that the performance we were seeing wasn't just due to the chance. To further assess the model fit, we generated a learning curve using cross-validation. The learning curve shows both the training RMSE and the validation RMSE as we increase the size of the training data. From this plot, we observed as the training set became larger, the validation error gradually decreased and then started to level off. At the same time, the gap between the training error and the validation error stayed relatively small. This pattern suggests that the model is not severely overfitting because the validation error does not blow up compared to the training error. It also suggests that the model has enough capacity to capture the underlying patterns in the data. The learning curve provides strong evidence that our XGBoost model achieves a good balance between bias and variance.
In the final part, I will summarize how we judged the model fit and explain why we finally select the XGBoost as our final model. Based on the learning curve and the cross-validation results, we concluded that the XGBoost model is reasonably well fitted. The training and validation errors converged to the similar value, and the validation RMSE stabilized as more training data is added. We also tried a few alternative approaches to double-check this conclusion. In particular, we experimented with a neural network model and an AutoML approach using H2O. Although the network training smoothly with the early stopping, its validation RMSE was higher than what we achieved with the tree-based models. We also noticed that its performance was worse on very high insurance charges, which suggests the potential underfitting in the upper tail of the distribution. The AutoML approach was useful as a robustness check. It produced competitive results, but it didn't consistently outperform our turned XGBoost model across the different validation folds. So when we considered the predictive performance, model stability, and interpretability together, we decided that the XGBoost pipelined with a log transformed target was the best overall choice for our final submission. Overall, our results suggest that the final model generalized well to unseen data and achieved a strong balance between accuracy and robustness, which make it suitable for this competition setting. Thank you for your watching.